As another example on Ampere's law, let us assume that we have a long conducting cylinder with inner radius A and outer radius B. So it is not like a solid wire, it is a cylinder and it is a hollow cylinder. So it is start from A to B. The cylinder carries the current out of the page. So the current is coming from the screen towards your eye, and the magnitude of the current density in the cross section is J equals C multiplied by R squared. So we have current density, not total current, and this current density is not uniform. It depends on the radius inside this cylinder, where C is 3 multiplied by 10 to the power 6 ampere over meter to the power 4, and R in meters. What is the magnetic field B at the dot, this point in the figure, which is at a radius 3 centimeters? We have A 2 centimeters and B is 4 centimeters, and the observation point here at the midway between A and B, so it is at 3 centimeters. So it is required to find out the magnetic field at this point. Okay. So if we want to find out the magnetic field at this point, we are going to draw Amperian loop, and a suitable Amperian loop in this case is a circle with a radius small r. The magnetic field B dot ds for a closed loop would equal mu naught the enclosed current. So it would be required to find out the enclosed current in this case. We put a concentric Amperian loop through the dot, this Amperian loop. We need to find the current in the area encircled by the loop. So we need to find the current in this dark blue area. The current in this area is effectively J, or the current density J, multiplied or integrated with respect to the surface. So we are going to apply Ampere's law. B dot ds equals mu naught I enclosed. It is required to find I enclosed. Here we have the current density J equals C multiplied by R squared. This is given, and C is 3 multiplied by 10 to the power 6 ampere per meter over 4. So the enclosed current the enclosed current I would be the integration of J dot the area. And the area in this case would be 2 by R dr, assuming that we have a small ring of width dr and its radius is r, so it is 2 by r, the circumference, multiplied by this thickness dr. This is the area or the incremental area here. So the enclosed current would be the integration from the starting of the cylinder to the observation point. The starting of the cylinder is at a radius a, and the observation point is at a point r. So the enclosed current would be 2 by c constant, and here r squared and r, so it is r cubed dr, and the integration from a to r. The integration of r cubic dr would be r to the power 4 over 4, and the limits of the integration is from a to r. Now by applying the limits of the integration, we obtain the enclosed current as pi c multiplied by r to the power 4 minus a to the power 4 over 2. This 2 and 4 would introduce 2 in the denominator. Okay? Alright, this is the included current or the enclosed current. Let us go back to Ampere's law. The integration of B dot ds would equal mu naught I enclosed. So B multiplied by 2 by R would equal mu naught multiplied by I enclosed, which is pi c r to the power 4 minus a to the power 4 over 2. Now let us calculate these values. C 3.0 multiplied 10 to the power 6, mu naught is 4 pi multiplied by 10 to the power minus 7. This is C. Where is this pi? This pi will be taken with this pi, and we have 2r here will move to the denominator, so it would be 4r. So this mu naught c over 4, and the radius at the observation point is 3 centimeters, so it is 0.03 multiplied by 0.03 to the power 4 minus a, which is 2 centimeters, 0.02 to the power 4. So in this case, the magnetic field is 2 multiplied by 10 to the power minus 5 Tesla. Okay? Now, the question is why we are putting this negative sign. This negative sign effectively, we assume that, or not we assume, we have the current is coming outside the screen. So the current, the direction of the current is coming outside the screen. And we have assumed the Amperian loop in clockwise. So if we are going to be in the clockwise and use our right hand rule, we will put our forefinger along the Amperian loop. We will find our thumb is inside the screen, not outside the screen. So the current of this Amperian loop is opposite to the direction of the original current. That's why we have a negative here. So as a magnitude, the magnitude of the magnetic field is this value. But as a direction, it is the reverse of this Amperian loop. So we assume the Amperian loop in clockwise, but the actual magnetic field is counterclockwise. That's why we have a negative. The magnetic field B at a point 3 centimeter from the center axis is 2 multiplied by 10 to the power minus 5 Tesla, and forms magnetic field lines that are direct opposite to our direction of integration. So it is not clockwise, it is actually counterclockwise. So we have assumed first the direction of the Amperian loop in any direction we want, and according to the result, if it is positive, so the magnetic field is at the same direction of the Amperian loop. If it is negative, so the magnetic field is opposite to the direction of the Amperian loop. Okay?